All right. Hello, everyone, and welcome to the 8th UQM meeting. So today we have only one speaker, but the talk will be a little bit longer, maybe 45 minutes or so. Without further ado, let me introduce the speaker. We are very happy to have Luca Delacretaz from University of Chicago. And he's gonna tell us about the breakdown of diffusion on the edge. Luca, take it away.
Okay, thanks. Thanks to everyone for tuning in, and especially thanks to Hassan for the organization. I think we can all agree that you were ahead of the curve with these virtual seminars. So I'll be talking about this work that was done with together with Paolo Glorioso, who's also a postdoc at the University of Chicago, and we put it a few weeks ago up on the archive. So I'll be taking a few breaks throughout the talk to engage participation and ask for questions, but you should also feel free to interrupt me at any time if you have questions. Okay, so let me start with a lightning summary of our proposal. So as we all know, the edge of quantum Hall systems have gapless excitations. We sometimes think of them in terms of Carroll-Luttinger channels or CFTs. And as theorists, we like to consider these this edge physics at zero temperature. But on the other hand, it's been known for a while that thermalization is crucial to explain experiments, which typically don't see all the edge modes that are predicted, but rather only the ones that are protected by symmetries, like charge or heat. So the idea is that all the other modes are basically damped when things thermalize. So thermalization implies that the edge at late times is described by some form of hydrodynamics. And the simple question I want to address today is, what is the hydrodynamic description of the edge? So the other input that's necessary for hydrodynamics is the symmetries. And I want to stress that I will not assume translation invariance. So momentum will not be a long-lived quantity here. The only symmetries I'm going to use are the anomalous U1 symmetry that leads to charge conservation. And later I'll talk about energy conservation as well. So the kind of naive expectation when you have this anomalous charge conservation on the edge is that you will get a chiral ballistic mode. So a mode that propagates, for example, right moving depending on the sign of the magnetic field. And that broadens diffusively. So there's a kind of, at finite temperature, you expect that there's some kind of diffusive damping of this mode. So what we'll see is that this does not happen because hydrodynamic interactions are irrelevant. They lead to a breakdown of this diffusive damping. And instead, the breakdown of diffusion drives the system to a new dissipative fixed point that's not diffusive, but rather in the KPZ universality class. I'll explain what this is. Which in particular has dynamic critical exponents z equal to 3/2. So there's still a chiral ballistic mode, but instead of being damped with exponents k squared, it's damped with this exponent. So another prediction of this KPZ universality is for transport. The prediction is that transport is singular on the edge. So for example, the optical conductivity as a function of frequency diverges at small frequency, like 1 over omega to the 1/3. So I want to stress here that this is this non-ellipticity is really for small frequencies, the smallest frequencies, and it's pretty rare to have this type of singular transport at low frequencies. Usually, precisely because of hydrodynamics, transport at small frequency is analytic, and instead the kind of interesting physics is in, for example, in the temperature dependence of transport. But here, this is really possible because of a breakdown, in some sense, of hydrodynamics. Okay, so these are our two main results. There's a number of extensions. We can talk about heat. I'll talk a bit about it, and we'll see that diffusion of heat also breaks down on the edge. And there's some generalizations to higher dimensions. For example, if you stack quantum Hall systems, you'll get the edge will become a surface. And these chiral surface metals also have interesting transport properties because of these fluctuations. So there's three kind of key things that come into this simple setup that I want you to take away. The first is that there's a hydrodynamic theory that describes a condensed matter system, but momentum is not the long-lived quantity. So you might have heard about the efforts in the experimental community to try to see kind of hydrodynamic flows in electron systems in the past few years. And it's really challenging there because you're always fighting against dirt, against momentum breaking processes, umklapp, and so on. Here, dirt is on our side because we're not assuming momentum as a long-lived quantity. Another important aspect of this system is that there's an anomaly. The U1 symmetry has a 1 + 1d chiral anomaly. So often anomalies lead to kind of subtle effects on transport. Here we'll see that it has dramatic consequences because it leads to this final point, namely large hydrodynamic fluctuations. All right, so before I get started, are there any questions on the general setup?
Question?
Yep.
What will this divergent optical conductivity mean for DC transport?
Yeah, that's a very good question. So it's going to be cut off by finite system size. It's important to stress that it's not the conductance of the full material. So it doesn't give, you know, a large, you would have to really measure the edge conductivity. But yeah, it's going to be large.
So it's some order of limits issue. If you have some, I don't know, 2-terminal or 4-terminal measurement, is that?
Yeah, that's right. This is cut off by finite system size. I mean, roughly speaking, you can think of finite system size as evaluating the correlation function at finite wave vector, and then that resolves this singularity.
Okay. Mm-hmm.
Any other questions? All right, so I'll start by explaining how these hydrodynamic fluctuations can be taken into account. Then we'll see how to apply this formalism to this chiral edge. And finally, I'll talk a bit about heat transport and experiments. Okay, so let's start with hydrodynamics. So any system that thermalizes, whether it's quantum or classical, is described by some form of hydrodynamics at sufficiently late times. And which hydrodynamic theory to apply just depends on the symmetries of your system. So for example, if you only have energy and charge conservation, typically what you get is a theory of diffusion. But if you have, say, momentum conservation, then you can land on the Navier-Stokes equation and so on. But really, only the symmetries matter. So two systems with the same symmetries will have the same hydrodynamic description. So the first question that comes to mind is, how is such a universality possible? And the kind of cartoon explanation for this is that at finite temperature, most excitations relax at a time scale that I'll call the thermalization time. But not everything can relax. Conserved quantities can't relax. The total charge can't relax, of course. So long wavelength modulation of conserved densities will decay with a rate that's small, that's proportional to their wave vector k. Okay, so as long as we take their wave vector to be small enough, we look at the long distance physics, these modes will be parametrically slower than generic excitations. So then hydrodynamics is just the late time description of these coarse grained quantities, the density, for example, coarse grained density. So let's see how this works in the simplest possible example. Let's say I have a single conservation law. This could come from a U1 symmetry or just energy conservation. So then hydrodynamics will be the theory of a conserved density that I'll call N. Or I could alternatively work with its associated potential. And so this density is subject to the conservation law, which also involves the current J. So the current itself is not a slow quantity. I don't know what it is. But at very late times, everything is only carried by everything thermalized. So everything that remains is the conserved quantities. So at late times, I can basically expand the current or any other operator in terms of my conserved densities. Okay, and I'll do this in a gradient expansion because I'm interested in the long distance physics. So the first term I can write down looks like this, and then there's going to be higher gradient terms. If I solve these two equations, what this will give is this kind of theory of diffusion with a diffusive Green's function. This is what the retarded Green's function looks like. D is the diffusion constant, chi is the charge susceptibility or compressibility. So it's important to note that there are two expansions going on here. The first is a gradient expansion. Okay, there are higher gradient terms here. So this expansion is always controlled, at least in principle, because I can always look at long enough distance physics, large wavelengths, and so these terms will be small. But there's another expansion, which is an expansion in the fluctuations, in higher powers of the density, for example. So here I could add terms with higher powers of the density. So this expansion is a bit more subtle, and it's only controlled when interactions are irrelevant. So how do we determine whether interactions are relevant or irrelevant? Well, there's a simple way to do that. Let me explain it. So in a diffusive system, this is what the diffusive correlation function looks like in space and time. So it looks like a Gaussian that's slowly spreading in time. And there's this overall power of time. You can guess this by simply remembering that if you integrate over all of space, total charge is conserved. And so you should get a constant. And that's what this integrating this, this Gaussian will do. So what we learned from this expression is that density scales with this power of time, or with frequency to the d over 4. D is the spatial dimension here, or like wave vector k to the d over 2. So the bottom line is that as long as the dimension is positive, nonlinear terms are going to be irrelevant or less relevant than the leading diffusive term. So for example, if I look at this nonlinear term, it has a higher power of charge density, so it's going to be irrelevant. But these terms are there generically. So for example, you could imagine expanding the diffusion constant. So diffusion constant generically will depend on temperature or density or whatever. And so expanding, just Taylor expanding it will lead to these nonlinear terms. So diagrammatically, your current will be allowed to decay into multiple charge excitations, one charge excitation or two charge excitations, and so on. So even though these terms are irrelevant, they still lead to two corrections to transport, which are small, but can be studied. This is the theory of hydrodynamic fluctuations, which has a long history. And so it leads to corrections. For example, the conductivity in a diffusive system to leading order is just a constant related to the diffusivity. But this nonlinear term will lead to a loop correction, a hydrodynamic loop that is non-analytic, but small. Okay, it's a small correction at small frequencies. And nevertheless, it's been seen numerically, for example, using exact diagonalization here. Okay, so this was the lightning overview of hydrodynamic fluctuations. Are there any questions about this? All right, so I'll move on to applying this to the chiral edge. So now we're basically solving the same equation, except we have an anomaly. That's the only difference. We have the 1 + 1 d-chiral anomaly, and the anomaly coefficient is related to the filling fraction in the bulk. I don't have the factors of 2 pi, etc. right here, but you can look in the paper if you want to see them. So I probably don't have to explain to this audience how anomaly inflow works, but this is kind of the picture for why there's charge is not strictly conserved on the edge. So it's been known for over a decade now how to incorporate anomalies in hydrodynamics. Basically, they fix terms in the constitutive relations. And so here, for example, this anomaly will fix a term in the constitutive relation for the current. This time I wrote it in terms of the chemical potential instead of the charge density. But this term here is the diffusive term that I already had before in my theory of diffusion. And now there's an extra term. Notice that it breaks parity, as it should, came from the anomaly. And its coefficient is fixed in terms of the anomaly. So if we plug this current back in the continuity relation, we'll get a kind of anomalous diffusion equation for charge. So there's this diffusive term. But there's this first term, which is a kind of chiral speed of sound, and the velocity is fixed in terms of the anomaly, but not universally. So it depends also on the compressibility. So you can again solve this equation linearly. You'll get a Green's function that looks like a chiral mode broadening diffusively. So if I have an initial pulse here on my edge, it's going to be, for example, right moving and broaden. So before we saw that the diffusion constant could depend on charge itself, and that would lead to nonlinear corrections to this story, but that they were irrelevant. Now, however, we have this more relevant term. We have the velocity, and the velocity can depend on charge. So the velocity of this edge mode is not universal, and it can depend on charge. So we'll have other nonlinear terms, a nonlinear term that looks like this, which seems a bit more dangerous because we started from a more relevant term. So let's see how relevant it is. So this is our anomalous diffusion equation. So let me just remind you that charge scales like k to the d over 2, which in one spatial dimension is k to the 1/2. So we have this first term that controls the chiral ballistic front. There's one power of charge and one gradient, so in total k to the 3/2. The diffusive term is down by one spatial gradient, so down by 1 power of k, whereas the nonlinearity, the interactions are down by 1 extra power of n, so k to the 1/2. So what we find is that these interactions are less relevant than the chiral front, so the existence of a chiral ballistic front will survive. However, they're more relevant than diffusion, than the leading dissipative effect. So they will lead to a breakdown of diffusion. Dissipation will not occur through diffusion in this system. We don't know how it's going to happen yet. So this also means that the hydrodynamic perturbative expansion breaks down. We don't have perturbation theory. So what should we do? Well, the first possibility would be to use some kind of dimensional regularization. So we could work in, for example, we could work in higher dimensions where fluctuations are weaker. And in fact, it is possible to expand from the upper critical dimension, which ends up being d = 2 spatial dimensions. And the theory, this kind of generalization of this theory to 2 dimensions is actually interesting in its own right because it describes these layered quantum Hall systems, chiral surface metals. So we discussed this in the paper, but I won't talk about it too much today. But can we be more ambitious and hope for an exact, for a kind of exact solution in d = 1? So if you work on quantum criticality, you would probably think that this is wishful thinking. You know, there's no small parameter in the game. Interactions are relevant. But there's some magic in 1+1 dimension and dissipative physics in 1 dimension, where even though it's not possible to exactly solve the critical point, some critical exponents can be obtained exactly, in particular the dynamic critical exponent z. And the earliest example I'm aware of this is in the Berger's equation that was found in this paper. Another famous example is the KPZ equation, which in fact is pretty much equivalent to this example. And slightly more recently, people found also that the Navier-Stokes equation in 1+1 dimension, some aspects of it can also be solved exactly and have share similar features. So it turns out that we will be lucky. This will be possible. In fact, we'll be able to map this equation to the KPZ equation. And the map is very simple. So the first step is simply to get rid of this speed of sound by working in the frame of the pulse. Okay. So then we just have this diffusive terminal and the nonlinearities. And then the charge simply maps to the slope in the KPZ equation, if you're familiar with the KPZ equation. Otherwise, it's not a problem. But this means that we can basically map this problem to the KPZ equation. So if you're familiar with this, you might know that there are also noise terms in these systems. This is stochastic physics, but the noise terms also map appropriately because they're fixed by fluctuation dissipation in terms of these diffusive terms. So the bottom line is that the edge of quantum Hall systems is in this Berger's KPZ universality class, which in particular has this z = 3/2 exact dynamic critical exponent. So let's see what the consequences of this are for our edge. So it means that our collective mode, charge fluctuations on the edge, propagate, have this kind of chiral ballistic propagation, and they spread with this k to the power 3/2. And the prefactor of this kind of dissipation is in fact completely fixed in terms of these thermodynamic parameters. So I really like this formula because it shows the 3 ingredients that were necessary to have this breakdown of diffusion. The first is the anomaly, mu. again, if we don't have an anomaly, then we'll just have regular diffusion. The second is temperature. So we need, thermalization and finite temperature. And the last one is these hydrodynamic nonlinearities that came from, the equation of state from things depending on charge in general. So here, the dependence of charge of the charge susceptibility, for example. And it's also pretty surprising that dissipation is completely fixed in terms of non-dissipative things. This is again some magic of KPZ scaling that ties dissipation to equilibrium thermodynamics. So what we have is this edge mode that still propagates chirally, but diffuses or dissipates with another power of K. So we can also look at transport in this system. So transport is controlled by current correlators or charge correlators. And these are, in the IR, will be completely fixed in terms of KPZ scaling function. So this scaling function is a universal function, a property of the KPZ fixed point. It's a whole function of a real parameter. And it's not known exactly, it can't be solved for exactly, but it's known numerically to a very high precision. And in particular, its limits are known. And so you can compute the connectivity as a function of frequency. And this is how you'll get this 1 over frequency to the 1/3. And the prefactor is, again, completely fixed in terms of numbers and other parameters that appeared before. Okay, so these are basically the two main predictions, singular transport and this anomalous damping. So if there are, maybe I'll pause for questions and then I'll talk about heat. Are there any questions about these results?
So Luca, you mentioned there is a non-chiral version of this, just in the comment. I'm guessing that's when there's not much relaxation between right and left moving modes. Is that
exactly?
Right?
Yeah, exactly. So they, in fact, in the deep IR, they just have diffusion, but they have an intermediate scale where you have a kind of KPZ-like scaling. So you can think of it as a kind of an approximate symmetry. There's some window where you see these two modes.
Right. So they observe it in some numerical calculation, or
yes, yes. This is some classical numerics. This paper, some spin chain with a kind of approximate emergent symmetry that leads to this extra mode.
So even in the classical, this is a purely classical model they're looking at. And
yes, yeah.
It still knows about this approximate chiral anomaly.
No, so they don't have a chiral anomaly. So their model is completely non-chiral. It's more like their sound. I think one way to think about this sound is kind of like a superfluid. So of course you don't have order in these systems, but you have some kind of, well, you could either think of it as an approximate, there are two ways to think about it. I think you could think of it as like approximate momentum conservation. Then you'll have regular sound, like in water, but it's only approximate. So in the deep IR, you just have diffusion. These intermediate scales, you have KPZ broadening of the
I see.
sound.
Thanks.
Question?
Okay, Max, go ahead.
So if I think about the CFT, what are the nonlinear interactions that contribute to thermalization? I mean, is it the cosine terms, or is it some sort of like dx pi to the 4th, or?
Exactly, right. Yeah, so if you have an exact CFT, CFTs in 2D don't thermalize in the usual sense. So if you have an exact CFT, none of this applies. But I think we can agree that conformal invariance is at best emergent in these systems. So there's going to be some cutoff, and some irrelevant operators will break conformal invariance, and it's these that will lead to thermalization. So there's some.
So it's some cosines, is that, or?
So you're saying in a Carroll-Oettinger liquid, for example?
Yeah.
Yeah. So there's one example of a mechanism is when you have several channels that are propagating in different directions. So this was actually done in the Kane and Fisher papers. And then you couple it to disorder, and that leads to some kind of small thermalization.
What about if you're like nu equal 1/3, if you're purely chiral? I mean, that seems to be the case that you are discussing here.
Yeah. Yeah, if it's purely chiral, so from the microscopics, it's less obvious whether it's going to thermalize or not if you start from a single channel Chiral-Oettinger liquid. But maybe that's not the best starting point. Is maybe how I would take it. So potentially a less kind of microscopic starting point would be to just say, well, I have charge conservation, I have this anomaly. And the true systems have Coulomb interactions, have a bunch of there's dirt, there's all these things. So it's not obvious that a pure single Chiral-Oettinger channel is the best model for it.
Well, it seems to me that you always have ultraviolet things that which depend on details of the interaction, and we know that typically something that is non-decay. If you have something that's integrable, it's usually integral only when everything is exactly right, and anything that on the microscopic scale changes it means eventually you're going to get deviations, and presumably that's what you need here. Although what power it is of cosine or whatever is
Exactly.
not obvious.
I understand that, but one question is whether it's like power law in temperature or it's exponentially small than 1/t. That could be. Yeah,
so that depends on the mechanism. In the kind of best case scenario for thermalization, where you have these counter-propagating modes and disorder, then you can just compute it, and there it's power law. In the case you're describing, I'm not sure if it's more specific.
Luca, maybe if you have a chiral mode with velocity that depends on the chemical potential, could it lead to this effect? The speed of light doesn't have to be constant and independent of chemical potential.
Right, exactly. Yeah. Here it's coming from the fact that the speed, you don't mean the literal speed of light, probably. You just mean the speed of light.
Well, if you have a chiral mode, it has some speed, right? But that speed may depend on the chemical potential.
Exactly, yeah.
So it's some dx phi to the fourth or some term like that.
Yeah, I think it's something that like what Glassman considered some time ago.
Mm-hmm. Any other questions? So again, the critical assumption is thermalization, and the question is, basically the assumption is that the thermalization time is short enough that that things thermalize on experimental timescales. All right, so let me talk about heat. First, if we just completely, treat heat and charge separately, then essentially we'll have two copies of what I just said. So basically, if we first neglect thermoelectric effects, charge will still propagate chirally with a velocity that's fixed by the filling divided by the susceptibility, or the bulk Hall connectivity divided by the susceptibility. And similarly, heat will propagate chirally with a velocity given by the thermal bulk, the thermal Hall connectivity divided by the specific heat. Okay, and so we'll have two modes propagating with different velocities, but both with KPZ spreading. So it might look something like this. Now, what happens if, generic systems have thermoelectric effects, charge and heat are coupled, but that actually doesn't change too much because interactions between these sound modes with different, or these kind of chiral sound modes with different velocities are just kinematically disfavored compared to self-interactions. The sound mode prefers to interact with several, self-interact with itself. So basically the conclusions are unchanged. So we'll have these two chiral modes with different velocities and with anomalous damping. So the thermal conductivity as a function of frequency will also have this singularity at small frequency, like 1 over frequency to the 1/3. So there's a special case that's pretty interesting, which is when the bulk thermal conductivity vanishes. This happens, for example, for nu equals 2/3. So in this case, the chiral velocity of heat vanishes, and the linearized kind of analysis would say that heat will simply diffuse, okay, like it does basically in any other material. So what's going to happen is that if I perturb my system, charge is going to propagate chirally like before, but heat is simply going to diffuse around the initial perturbation. So one can ask, does this prediction survive hydrodynamic fluctuations? And the answer is a bit more subtle, but it probably doesn't. So let's see what happens. So heat doesn't have a speed anymore, it just diffuses. And because it doesn't have a velocity, remember the leading interactions came from the fact that the velocity depended on the density itself. So it won't have these kind of leading interactions that led to KPZ physics. However, it will interact with the charge mode, which itself has KPZ physics. Okay. So as I said before, these interactions are a bit less relevant because in some sense, the charge mode is far off shell. But they still do something. And actually what they do turns out to be an open problem in the field of stochastic physics. But there's some approximations one can use. There's this so-called mode coupling approximation, which basically amounts to trying to solve this kind of self-consistently. And this approximation predicts a dynamic critical exponent of 5/3. So this would suggest that heat, instead of diffusing, spreads in this way. Okay, and the thermal conductivity is also singular at small frequencies, but a bit less singular than charge. All right, so let me talk a bit about experiments. Okay, looks like I still have some time left. So our two main predictions are the singular low frequency edge transport and the anomalous damping of these edge modes. It's difficult to measure the conductivity of a single edge. And so that's actually another reason that led us to study these layered quantum Hall systems and chiral surface metals, because then you could imagine shining light on these edges. But actually, something that seems much more promising is this damping of these edge modes, because they've been observed in a number of systems for a while, in particular in gallium arsenide, but also more recently in graphene and cold atoms. So people basically just send a pulse on their system and then measure the pulse coming out on another end. This has been also done in graphene. Here in cold atoms, you can basically, you can visualize the motion of charge along the edge. The charge is moving chirally. And the damping of this mode is called the edge magnetoplasmon. And its damping has been studied to a certain extent. In particular, the linear dependence on filling has been widely observed in these systems. The temperature dependence hasn't been studied too systematically, but it seems consistent with a rather weak temperature dependence that we predict. But probably our most striking prediction is this dependence on wave vector. And we searched a lot through the literature. There isn't a lot. We basically didn't find any paper that reported wave vector dependence, except for one very old paper from '94. So maybe it should be taken with a grain of salt, I don't know. But we were very excited to see that in their abstract, they say that the magnitude of the damping increases with frequency, the dependence somewhere between linear and quadratic, which would nicely agree with this. But my experimentalist colleagues tell me that I should be careful with these old experimental papers. But it would be very nice to see it in these newer experiments, in particular in these other systems. Let me also comment on the heat mode. So the heat mode, since it's neutral, is harder to study experimentally. But there has been a lot of progress in the past decade or so, in particular in this special case where the bulk thermal Hall connectivity vanishes. Because in this case, as we saw, the heat doesn't propagate chirally. And so it's basically the only thing that can move upstream. Okay, this is called upstream heat transport. And so because of that, there's a chance to kind of see it. And so these more recent experiments have been creative in trying to detect this upstream propagation of heat, and apparently they've seen it. In this experiment, they were even able to use this detection of the heat mode to show that they had edge reconstruction. So they had a nu = 1 state, and they observed a heat mode that you would expect in the 2/3 state. So they say that they have edge reconstruction in this system. All right. Okay, so I'm basically done. Maybe just a few points that I want to add. So here I focused on the edge modes of quantum Hall systems, but we expect this to apply more generally whenever you have protected edge modes that are protected against thermalization. In particular, in our paper, we even discussed higher dimensional generalization of these effects. You could, of course, have more symmetries. Here I tried to be kind of minimalist in terms of the symmetries I assumed, but I could have more internal symmetries or space-time symmetries. For example, you could have a bigger group. You know, if you really trust your experimentalist friends a lot, you could decide to add momentum to one of the slow, you know, degrees of freedom in your hydrodynamics. In this case, you won't be protected from the KPZ fate of these modes. All that will happen is that you'll have more long-lived excitations, but they will also have KPZ spreading generically. And lastly, let me just briefly connect to this recent nu equals 5/2 controversy that maybe some of you have been following. So there, the thermal Hall connectivity doesn't seem to match the expectations depending on which states you prefer. And some people proposed a resolution by saying that the edge doesn't thermalize. So here we saw an inevitable consequence of thermalization. So it could be used as a way to, you know, to decide whether the edge really does thermalize or not. Okay, so thanks a lot for for listening. I put my email address here in case you still have questions or comments that you didn't have the chance to ask.
Thank you very much, Luca, for this interesting talk. So we have time now for questions. Okay, I have a question. So is it possible to generalize this to like chiral superconductors? Let's say we want to give up the charge conservation. I don't know.
Yeah, that's a good question. So I think, I mean, it all depends whether you have an edge mode with I would say as soon as you have an edge mode with some velocity and that this edge mode does not get damped from thermal, you know, at finite temperature, then it's hard to avoid this.
I see.
So this edge mode would transport only heat, but not charge. Can you have a situation which has only conservation of energy, but not charge?
I guess so, actually. I don't know. Are there, you could imagine a system with a bulk thermal Hall connectivity that's gapped, but that just doesn't have, I don't know, does this exist?
Yeah, like a PX plus
that's
superconductor. Yeah.
That's the kind of superconductor.
Okay.
Right.
So what would happen then?
There'll always be phonons. Heat is never perfectly conserved. There'll always be some substrate phonons. There'll be at finite temperatures, you have always some quasi-particles excited above the gap and so forth. So that's going to be at best approximate.
That's a good point. So heat doesn't have as robust a status as charge. It can leak out of the edge. But the hope is that it's a pretty different mechanism that leads to thermalization than the mechanism that leads to, you know, energy non-conservation. So there might be a window where you can see this.
I think the point is you can have damn good insulators.
Right.
So I had a question, Luca.
Mm-hmm.
You know, you can think of, you know, this was the 1+1D case. You can think of a 3+1D analog, which is wild fermions, which also have a chiral anomaly.
Mm-hmm.
Do you think there's some analog of this for that kind of anomaly?
Yes, so there is, but the hydrodynamic fluctuations are less relevant. In fact, they're irrelevant.
Mm-hmm.
So but there are long time tail corrections that will come from this. I mean, one simple example is the chiral magnetic effect, where, I mean, you start, you know, you have, let's say I turn on a magnetic field then basically along the field lines, I have this physics. But again, the wave vector can go in all directions. So there, it's less relevant. In fact, it's irrelevant, but it leads to corrections to transport.
I see.
I have a question. What is the status of experiments on nu equals 2/3 quantum Hall states? Are they understood? I remember there were some mysteries, and does this explain any of them?
Oh, I wasn't aware of the mysteries. So I don't know. Maybe someone else knows.
So I think in Heidboom's experiment, they have for nu equals 2/3, there is some anomalies in the data. But the fit is less works less well than the other fraction. Is that what you mean, John?
Yes, that's right. Yeah.
I have one other quick question. So when you say higher dimensions, you mean just stacking chiral modes, or like something like in 3+1, for example, your boundary is a surface, and then like something like a while point, is that, so that also has its own anomaly, but maybe it's
right. Yeah, I was thinking just more generally of situations where you have a mode propagating ballistically in some direction. So it's, I wasn't thinking really of isotropic systems. So there's some preferred direction, like when you stack, or like in the chiral magnetic effect when you have field lines. And then there's spreading around that front.
I see.
So just to follow up on Hassan's question, you said you had some results for the chiral metal. How do they differ from this, the 1D case?
Good, yeah. Actually, I might have some slides on this. So in the, actually, let me first say, so in the chiral metal, the interaction is marginal. It has the same power. Let's see if it works. Yes. If D equals 2, yeah, exactly. It has the same power as as diffusion. So interactions are naively marginal, and it turns out that they're marginally irrelevant. So you still have perturbative control on the system. In fact, that's why you could even use it as an upper critical dimension to reach the KPZ fixed points. But if you're interested in 2D, then you can just kind of resum the logs and get and find a result that looks, you'll get logarithmic corrections to transport. I don't think I have the final result here, but we have it somewhere in the paper, which roughly looks like, it basically looks like a diffusion constant that depends on log omega.
I see. And do you think this would hold for these Fermi arc surface states of a wild semi-metal? There's some gapless excitations in the bulk as well.
Yeah.
They could have a very small density of states if you're looking.
Right, yeah. I think it would hold, but would be harder to detect maybe. But I think it should hold.
In the Fermi arc case, you probably need momentum conservation as well, right?
At least perpendicular to the you mean to define the two wild points.
Right.
Although this could be in a different direction. I mean, you could have, in principle, you could have momentum conservation in that direction, but not perpendicular.
You could do this with momentum conservation in 2D. So you'll have, it still holds that interactions will be marginally irrelevant. In fact, in this paper, they studied just regular, hydrodynamics in 2+1 dimension, and it's very similar. Interactions are marginally irrelevant, and they can just resum the logs. So here you could add, exact or approximate translation symmetry if you want.
I see. So it shows up even just in transport in 2D.
Exactly, yeah. In 2D transport with exact momentum conservation, it shows up. Yeah. But any kind of disorder, weak relaxation of momentum will kind of cut off these loops and change the story. In that case, for them.
In a 2D case, it's typically described, I think, as coupling to long-lived viscous modes. So let's say if you have a density correlation, a fluctuation in the density, but you also have long-lived thermally excited viscous modes with transport perpendicular to the transverse modes, along with transverse modes. That's what gives you the logarithmic divergences.
Right, yeah. This viscous mode is momentum, basically, momentum density.
Yeah.
I have a question to Luca. Maybe also to Bert. I think Luca, you mentioned. Can you hear me?
Yes, I can hear you.
You mentioned this work may have an interpretation to the new code 5-half. And can you say a few words? Do you, for example, can support or rule out the interpretations from the Steve Simon?
Right. So I think the connection to me is simply that this nu equals 5-half story has put under question the assumption of thermalization, and so I don't think I don't think the fact that diffusion breaks down has anything to do with lack of thermalization. On the contrary, for all of this to apply, I'm assuming thermalization. But the hope is that here, by kind of studying the inevitable consequences of thermalization, we'll be able to test whether it's a good assumption or not in these systems. So you could imagine that it's possible to see this KPZ scaling in some edges, but not in others. For example, not in the 5-half for some reason.
But
does that answer? Well, it's a pretty open-ended answer, but
what do you suggest to check in order to maybe rule out the claim of Simon or favor the anti-Fabian state?
Okay, so I'm a theorist, so I can speculate a bit, but yeah, I would say, so in fact, it's been done in simpler systems where you basically study the damping of these edge modes. You can see these edge modes in a lot of these states, and try to find for example, study the damping, how the damping depends on temperature, filling, and wave vector. And so, for example, if you find a wave vector dependence of the damping that goes like k to the 3/2, that's a very strong indication that indeed the mode has thermalized and that it has this KPZ physics. So I wouldn't start with the 5-half state. I would start with some simpler states. But you could imagine a situation where you do see this type of damping in some situations where it thermalizes, but not in others. And that would be strong evidence that indeed the 5-halves, that for example, the 5-half state doesn't thermalize.
I think I certainly don't understand Heibloom's experiments, but I would say that there are a lot of things you can think about doing experimentally to help clarify it. There are things you can do, since we don't need to worry about momentum conservation. There are a lot of things you can do, like putting stuff on the edge or changing the edge in various ways to try to encourage thermalization, to make sure it does happen, and see if that changes the results. But these are not trivial experiments, and there are not very many people in the world able or willing to do it. So not happening rapidly, but I think eventually there'll be more experiments by just changing the geometry, changing features that they may not have to do with asymptopia the way we're looking at here, but will tell us whether he's really in the thermalized regime.
All right. If there is no other question, let's thank Luca again, and thank you everyone for tuning in. So we'll have our next meeting in 2 weeks, and hope everyone will stay safe and healthy. So we are still seeking for new speakers. So if you're interested in giving a talk, please email me or sign up on the Google Sheet. Thanks, everyone.
Thank you.